Okay, now a new article, light intensity. Okay, and the article, the title is written here as you see, light intensity of a diffraction pattern formed by a slit. As you know, this is the diffraction pattern, okay? I am going to draw it here. This is the laser beam, which is cylindrical, and here this is the slit. This is an enlarged figure of the slit. The slit is of order of 1 millimeter, yani it is like a point. Now, I am going to call this point I. The orthogonal projection of I on the screen, I am going to call it O. And as you know here, you have alternating dark and bright fringes. Alternating dark and bright fringes. Don't forget, the diffraction pattern is symmetric with respect to O, to the center of the central bright fringe. So these are the bright fringes and they have size, whereas the dark fringes can be considered as points. As we said previously, I considered this as sine theta axis for any angle, whether small or large. But for small angles, since sine theta is approximately equal to theta in radian, I can consider this also as theta in radian axis, so that I can define the position of the dark fringes. This is the first dark. K is equal to 1. Okay, and its abscissa is lambda over A. Now, the second one is 2 lambda over A. Similarly, you have here minus 2 lambda minus 1 lambda over A, because first dark, and this is minus 2 lambda over A, second dark. Okay, this corresponds to order 1, this is order 2, this is order minus 1, and here this is order, and so on. Now, the brightness of the fringes vary from one fringe to another. Okay? This brightness at any point on the fringe is determined by a factor called light intensity. Okay? The intensity. As you know, light will reach this region. So at every point here, at every point on the diffraction pattern, there is intensity of light. Why? Because every point here is receiving energy from light. As you know, light is a wave, and a wave carries energy. So at each point here, at each point, there is energy received I am going to call it, to write it as energy received, okay, by a point on the diffraction pattern, on the diffraction pattern. If there is energy received, then there is a power received. And the power received, as you know, at every point is equal to the energy received over time t. Okay? In SI unit, this is in joule, this is in second, this is in watt. Okay? Now, what is the intensity of light? The intensity of light, by definition, or the intensity received, the intensity at specific point is equal to the power received, okay, per unit area. This is in watt. You get this in meter square. So the energy received is watt per meter square here. This is called in SI system. So as you see, if the power received at a point increases, the intensity increases, and the brightness of the fringes increases. Okay? Previously, notice here, this figure. You see that the brightness of the central bright fringe is more than that of the first bright fringe. And as you move away from the central fringe, the brightness decreases till it becomes zero. When it becomes zero, you see nothing. Okay? So, let's study. I want to study the variation of the intensity of light at the fringes with theta, yani with the distribution of the fringes. To do this, look at this figure. Okay. Look at this figure. This figure is the graph of the intensity. Intensity along the screen, the intensity of light varies in this way. Okay? Let's see how to draw this figure of intensity. I am going to take intensity axis of center O, intensity I. Okay? This is only point I. This is represent the intensity in watt per meter square. This is a point. How to get this graph qualitatively without equation? The central bright fringe, this one, it is more intense, its intensity is maximum at its center. Okay, so at the center, this is the intensity, it is maximum. Let us draw it here. At O, at the center of the central bright fringe, the intensity is maximum. I am going to call it I node. Okay? As you move away from O on both sides, this intensity decreases. How do I know this? I know this because when I reach this point is dark fringe, so the intensity at this point is 0. Because of this, as we move from O to this point, the intensity decreases from maximum to 0. So let's draw. At all, intensity is maximum. As you move up, as theta increases, intensity decreases till 0. So I am drawing the graph. It decreases from maximum to 0. Okay? Now, as we move, as theta increases, we enter to the second bright fringe. Okay? So there is intensity. The intensity will increase. Okay? And will be maximum at the center. So here the graph will be like this. Okay, this is the center. The graph increases to maximum, but there is decrease in the intensity here. Okay, to maximum. Then as theta increases, the intensity also decreases till it reaches 0 because it is dark. So I move the curve from maximum at this point to 0. The same here. Then I enter through a bright fringe, okay, which is away, more away. So the intensity more away from O. So the intensity is also decreases, and so on till the intensity becomes 0. Similarly below, so you get here a symmetric figure, and I am going to call this the intensity of the maximum at the center. I am going to call it I1. This one, the intensity is maximum at the center, but this is for the second bright fringe. I am going to call it I2. So similarly here, the intensity decreases from maximum to 0. Okay? Then it increases to become maximum at the center. Okay? So here it decreases to become maximum at the center, then 0, then maximum at the center of intensity I2. So it increases till intensity I2, and here you get the variation of the intensity with sine theta or theta, okay, which is the same as this figure. So here, as you see, the intensity is maximum at the center, okay? It decreases to 0, then it increases, but observe the intensity here at the center is very low compared to the intensity at the central bright fringe. It decreases a lot. Also here, as you move to this one, also the intensity is less than this one, and so on till the intensity becomes 0 and the fringes will not be seen anymore. What is the difference between this figure and this one? This figure is the same as this one, but here it is rotated 45, okay? So that instead of taking, this is the y-axis becomes vertical, and the theta axis or sine theta axis becomes horizontal, as you see here. Okay, this is theta 1 of the first dark theta 2 of the second, theta 3, and here this is for small theta, the figure. What I want to say about the intensity, look here. This is the intensity at the center of the first bright fringe. And it is written here that this intensity, that I call it I1, it is equal to 0.047 from I node, from the intensity of at the center of the central bright fringe. Yani, we can write I1 equal 4.7% from I node, or approximately equal 5% from I node. Yani, notice here, the intensity from the center to the first, at the center of the first bright is decreased 95% from I node. Yani, a lot of power has dissipated here. Okay, because of the distance from here to here. Now, if I take I2, what is the intensity, which is not written here? The intensity at the center of the second bright fringe, it is equal to 0.017 I node. Yani, equal approximately 1.7 I node. Only 1.7% from the intensity at the center remains at the center of the second bright fringe, which a lot of loss of the intensity of light. And because of this, you see that the brightness of the dark fringe decreases sharply as you move away from the center of the central bright fringe. Okay. We have finished well the experimental and the theoretical study of diffraction by a slit. Now I am going to talk about the diffraction by thin edges, or by thin obstacles, like the diffraction by a hair or thin wire. فإذن diffraction by thin obstacles. Thin obstacles, example here, you have thin wire or hair. Okay, look at diffraction by a thin obstacle, a hair, or look at the diffraction by the hair. Okay, what do you observe here? You observe this diffraction pattern, which is similar to that of the slit. So the equation of diffraction to determine the angular positions of dark fringes for the slit are used the same for thin obstacles. So I am going to write them, which are the same. But what should you change in them? فإذن الأنgular positions for dark fringes are given by sine theta equal k lambda over, I am going to call it D, or you can keep it A, but in order to distinguish between them. And also K here is plus minus 1, minus 1, plus minus 2, plus minus 3, etc. Or K belong to Z star. Also for a small theta, you can write sine theta is approximately theta in radian, and you get here theta radian is equal K lambda over D, where K is the same as this. The difference here, you replace the A, the width of the slit A, by the diameter of the hair, okay? So D here is the diameter of the thin obstacle. As you see, this is the diameter of the hair. This is the hair. And this is D, okay? That's all. Now, I am going to talk about diffraction by small circular hole. Okay, let's see. This is the diffraction by small circular hole, and we talked about it previously. Because the hole is small, it is of the order of 1 millimeter, يعني 1 millimeter and less. When light passes through such small circular holes, it deviates from its original path, as we said. This deviation is accompanied, as you see, by central bright disk surrounded by concentric dark and bright fringes. All these fringes or circular spots of light have the same center as that of the disk. Look here, these are two forms of fringes. Both consist of central bright fringe and concentric fringes, alternating bright and dark concentric fringes. But as you see, this one is clearer than this. Why? Here, A or diameter of the hole is less than this. As the diameter decreases, the diffraction increases and becomes stronger. Okay? So, how to determine the position of the dark fringes in this case? Look at this figure. These are the dark fringes, okay? And this is the hole that acts as a point because its diameter is less than 1 millimeter or of order of 1 millimeter. This is the horizontal direction, and this is the angle of diffraction. So if I take the first dark fringe here, I draw a line from the hole to the first dark fringe, which is this one. I take the second, this is the dark fringe. So I draw a line from the hole to the first dark fringe. This is the horizontal direction, and this will be theta 1, the angle of diffraction of the first dark fringe. As you see here, this is the fringe is circular, so there is only one theta 1, not like that of a slit. You have theta 1 positive and symmetric one which is negative. Here you have only theta 1 is the angle of diffraction of the whole bright fringe, and you can take it from the hole to any point on this dark fringe. Okay? This theta 1 is given, is given by the formula first dark fringe is given by theta 1 equal 1.22 lambda over d, where d is the diameter of the hole. This is d, okay? Well, lambda is the wavelength of the monochromatic light. This must be of same unit. Yani if this is meter, micrometer, micrometer, and the angle theta 1 is in radian. Okay? The second dark fringe is determined by drawing a line from the hole to the second dark fringe, to the center of the second dark fringe, and this will be theta 2, okay? Theta 2, so second dark fringe, theta 2 in radian is equal to 2.23 lambda over d, and here d is the diameter of the circular hole, okay? Fine. Now I can find the angular width of the central bright fringe. The angular width of the central bright fringe, okay, which is denoted by alpha, as you see. If I draw, this is the central bright fringe, as we said there, and here this is theta 1, which corresponds to the angular position of the first dark, okay? Heidi first bright. The white color here is the first dark, and I said there, this is theta 1, okay? Also here, if I draw a line here, this is also theta 1, okay? And this distance is the diameter of the central bright fringe, okay? The diameter of the central bright fringe, okay? The angle facing this diameter is called the angular width of the central bright fringe alpha, which is equal to 2 theta 1, okay? Yani alpha is equal to times 1.22 lambda over d, okay? Notice here, as d decreases, theta 1, theta 2, alpha increases, which means that diffraction increases. Okay, see you. This is the end of the chapter.